Thanks. Okay, so I'm going to talk about the timer isn't, so I don't know how much time I have. Good. Okay, I'll just, you're stuck. I'm going to talk about this beautiful result of Ulrich Habok from Polygon Labs and David Levitt and Shahar Papini from StarkWare. But before I get to it, I'm actually going to talk about a bunch of other things, and this will probably be the least algebraic and least mathy talk you've seen so far. One of the reasons is that I've over the years veered a little bit further from math. So, you know, the less time I spend on it, the more I'll be able to fool you that you know, I understand it in a deep enough way. And I just want to comment generally that like math is one of those things, right? There's this famous saying that, you know, you never quite understand math, you can get used to it. And I really empathize with that. Even those results that I obtained in my career, I can't really say that I understand them on some very deep level. Just to give one example, you know, we talk about polynomials and we all view them as these squiggly lines, usually do like 3 or 4 times, but of course, we're working usually over these finite fields, so they have no such structure. And like, what are these mysterious objects anyways, and why do they show up and solve the problems they solve? There's something utterly mysterious and magical about it. So I'm going to, first of all, remind those of you, because I'm assuming some of you are not necessarily versed in blockchains and rollups and so on. So why are we even solving these problems? Or why is a conference done one day before like the Science of Blockchain conference, you know, dealing with algebra? Then I'll say a little bit about how the Circle Start result came about, at least from our point of view, like why was this motivated? Was motivated by questions of efficiency. And then I'll try to explain a little bit about what is Circle Start. And then with 2 questions, I have 30 minutes? Okay, cool. I thought 25, okay. It's less than that. Yeah. So I'll start with like why Stark and a little bit about scaling and how proofs go very well with blockchains. So both blockchains and proofs are related to integrity, which has been beautifully defined by C.S. Lewis as doing the right thing even when no one is watching. And really blockchains offer, or this, you can think of them as establishing this sort of universal or global PC in the sense of like a you know, personal computer, some reasonably strong but not too strong computer that is extremely trusted and has just immense integrity, which is why we entrust with it. Well, as of 2 days ago, you could say you entrusted with it whatever, over $1.5 trillion. As of this morning, it's I don't know, like $500 billion. But or whatever it is, but it's still a lot of value is entrusted with this, like, you know, set of technologies, this one PC. And how is it achieved? It is achieved by a absolutely magical, you know, another thing I don't quite understand, but I got used to, or we got used to, the world got used to, combination of transparency, distributed computation, and some game theoretic incentives, right? That of course Satoshi Nakamoto first unleashed. Okay, so we get this like PC, this weak computer that we trust, and we would like to put it to work on a lot of things. And the question now is, how do we scale it? Because it turns out that you can't just replace this PC easily under the same principles with, let's say, a supercomputer. It won't work. It would lose integrity. Part of the way it works is like everyone is supposed to use their own PCs in order to track it. So that won't work. So, and this is where cryptographic proofs come in. And there's this like prophetic line from one of the early works, a very important work, that talks about scaling computation or scaling integrity. So I'll read it. This is the work of Babai, Fortnow, Levin, and Segedi, which says, in this setup, if you have a single reliable PC, it can monitor the operation of a herd of supercomputers working with possibly extremely powerful but unreliable software and untested hardware. So basically a little bit like Archimedes said, you know, give me like a point that I could lift or move the earth. If you have like one reliable weak computer using, you know, some more math, and cryptography, you can actually use it to put in check some immense amount of computation that you have no assumptions about its integrity. And really, this is the connection of blockchains to cryptographic proofs. So, I mean, there are like two very different methods that solve the same problem. So they work together really well. And here's a very abridged history. So Zk has been around, for 40 years almost. I'll mention, I first heard this from Madhu when I was doing my postdoc with him. He said about Reed-Solomon codes that it took about, I think, 30 years from their invention to when they were first put in use, like on CDs. And it's curious that like the first general purpose usage of zero knowledge, meaning general purpose for general computation, was as a product, as an end user product, was in the Zcash protocol, really like 31 years later. And PCP techniques then used for, which also came sort of the late 90s, the early 90s, put to use as a scalability solution by StarkWare. This is what, we were among the first to do in 2018. Now, what we've done, StarkWare, we've demonstrated to the world that this particular set of technologies is actually really, really good at solving the problem of scale. And by now, it's been adopted by almost all of the scaling solutions that use these validity proofs on top of blockchain. So 3 Polygon teams, RISC-0, Succinct, ZK Sync, and us, they're all using Starks. And the power, the force that really showed it is this, for us at least, it's called this stone prover that's been around for a while, which is how we're going to get to Circle Stark. So we've settled a lot of transactions, saved a lot of value for customers using this technology based on cryptographic proofs. And I just want to explain how it roughly works. So if you have your chain, which is this very trusted computer, but is running very, very slowly, so it costs a lot to put computation on it, well, you could maintain a state that is much greater. And let's say it could also be captured just by a hash of the most latest state of accounts. And what you do is you get your transactions actually off-chain. They never appear on-chain. And you sequence them into blocks. And then what you do is you run these blocks, you generate proofs for them. And the proofs are very succinct in their verification time and resources that are needed. And then what you do is you send them to, we have this PC that's very trusted, which is the blockchain. So what we do is we send to this PC, we send the proofs. The proofs are much, much shorter than the amount of computation they attest to. The verifier checks that the proof is okay. And because of the math and cryptography, we know that everything really was done with integrity. So we can now update the state. And this is the way all of these systems work. So this is a brief explanation of why Stark or why cryptographic proofs are important in the context of scaling blockchains. Now, what is the motivation for Circle Stark, which is the stuff I'm going to tell you about in a little bit. So I told you that Stone was it stands for like Stark 1. It was the first generation prover that we used. It's already been in production for 4 years. So it's like one of those, Boeing 747s that hauls a lot of stuff, but its technology is already by now 4 years old, and its design is 5 to 6 years old. And the biggest thing to know about it, or the one that is, I would say if you talk about places to improve, it is constructed over a prime field that is very large. It's a 252-bit prime field. And the reason for that was that if you look at the main cost that we were trying to optimize, it is the cost of verifying things on Ethereum. Ethereum is designed so that all integers are treated the same as long as they're less than 256. So you don't need to save on this important resource. And the second thing is that it also leads to simpler auxiliary cryptography. If you want to do things like elliptic curve signatures and stuff like that, it's simpler to construct them over these large prime fields. So for these two reasons, we just started with this very large prime, even though it's not needed in the world of Starks. Another thing is that the infrastructure is by now kind of old, and we know how to do things better, which means that we said, okay, about like a year and a half ago, we said, okay, it's time to now come up with, or basically build a new prover. And so much has progressed. For instance, we know how to move, just like Swastik was explaining, we know how to move beyond fields that have subgroups that are FFT friendly. There are also like new arithmetization techniques that let you speed up things like, log up of, again, of Uli Chabok, one of the authors of this. And we know how to even merge together things like univariate and multivariate polynomials, the stuff that is used for sum checks that Yael referred to in her call, so in her talk. So you can basically unleash like new kinds of arithmetizations, and also even just the task of taking computation and baking it into constraints. We know how to do it a lot better. And now, actually, the programming language that everyone loves is actually Rust, not C++. So yet another reason to revisit things. Okay, so what did we want? We wanted an efficient Stark in terms of proving costs and other costs, and we wanted to run really fast over commodity CPUs and GPUs. And then this pretty much leads you to work with 32-bit words. Why? Because CPUs and GPUs, that's like even though they can operate also on 64-bit words, they're much faster on 32-bit words, and they're not that much faster on smaller things. Now, another thing to notice is that integer arithmetic is supported very efficiently on both CPUs and GPUs for historical reasons, whereas binary convolution, which corresponds to binary field multiplication, is currently not as well supported on GPUs. It's very well supported on CPUs, but not on GPUs. Now, the talk after me is actually going to be about using binary fields, which I personally love a lot. It's the Irreducible team will speak about that. So, curious to hear their take also on this. We decided to go among all the design choices with a 32-bit integer prime field, right? For these reasons. And indeed, just jumping to the end, we already released like 2 weeks ago that we can now, broke the world record in terms of proving capacity, proving over 500,000 invocations of a hash, a Stark-friendly hash, which is 100x better than anything the world has known prior to that, at least the best of what I'm aware of. But I just want to mention, I'm sure that this will not remain the world record, and there are a lot of proof systems, most of them over small fields, that will be this, this is not going to stay this way. So which 32-bit field should we take? Well, there was already one in use called Baby Bear, which is this particular prime, 2 to the 27 times 15 plus 1. And if you look at its multiplicative group, so the size of the multiplicative group of a field is always 1 less than the size of the group, you get the size that is 2 to the 27 times 15, which means that there's an FFT-friendly group of size 2 to the 27, which is why, for instance, RISC-0 took it and worked with it, and a bunch of other teams. So it's a really good prime. But there's actually one that is even cooler, M31, which is the Mersenne prime 2 to the 31 minus 1. And the reason it is cooler is that it allows for very fast multiplication on commodity CPUs and hopefully also GPUs, because 2 to the 31 equals 1. So you can do all kinds of like shifts and so on. And so it turns out to be roughly 30% faster multiplication. But the problem is that it does not have an FFT-friendly subfield. So what do you do? So this is the motivation for Circle Stark, right? We want to work with this particular field because it's like really efficient, but it doesn't have the necessary structure. And why do we need FFTs? By now, I think, because the previous talks already mentioned it, you get faster encoding, you get FRI, and it's really important if you want really efficient algorithms. Okay, so which group are we going to use? So all of these groups are cyclic groups. Well, first of all, let's realize that it cannot be the native subgroup of M31, because this is the size of that multiplicative group, 2 times 9 times. So if you think about FFT, you don't have really a very good structure here to do FFTs with. Now, as Swastik already pointed out, there was the option to use some elliptic curve, to go and look for an elliptic curve over this field that it will have size divisible, let's say, by 2 to the 30 or maybe 2 to the 29 or something like that. And then you would get some other group that would be more complicated. So it won't be already powers, but it will be like this evolution of points where each point is two numbers by some complex formula. And it gets even more complicated because like the kind of FFT reductions in the ECFFT paper call for a sequence of different curves. So it's a bit more messy to work with. And which is how these three brilliant individuals came about to this thing, to take a different curve, which is the circle, the good old circle. If it was over the reals, it would actually have this picture, but it's not quite that way there. So it's all pairs of points that when you square them and add them up, modulo this Mersenne prime, you get 1. So for instance, one of these points is the point, 2 to the 15, 2 to the 15. And but again, we sort of fool ourselves, or we get used to it and we think of it as sitting on the circle. And you get something that is much nicer in terms of its FFT friendliness. And now I want to explain a little bit about what is nicer about it, and also a little bit about the complications. So now we'll get a little bit more into the math of what do we mean, what is this circle Stark? Actually, will be mostly about the structure of this group and how to work with it and what kind of functions are we going to evaluate using it, okay? Any questions so far? Okay, so going back, I started by saying that the use of polynomials and similar critters in the construction of proofs is utterly mysterious to me. I don't really understand, but there's a pretty long collection of properties that each one of them makes an appearance, and you need all of them, and magically or mysteriously, polynomials happen to have them. They're not the only set of creatures that have them. There are a bunch of other algebraic creatures that happen to possess them. So one is their error correction properties, which, and all of these were mentioned in some form or another in all of the talks before. So the polynomials form the basis for error correcting codes. Here's another thing that wasn't mentioned, I think, but is really important for constructing statements about computation. You would like, if you wrote down, let's say, an array that corresponds to the evaluation of a polynomial. Well, there are certain permutations that you can apply to this array, and you will still get a polynomial. So for instance, for polynomials, if I have p of x, I can move to p of ax plus b for fixed a and b, which means that I will sort of permute the values, and it's still a polynomial. And this is a very important property because it allows us basically, when we talk about computation, usually we want to talk about something that examines both a certain point in time and a point later in time. And in order to do this, it turns out that you really want your error correcting code to have this sort of property that you can move things around and still work with the same objects. So you actually need this automorphism group, which is this ability to permute things around. They also have the multiplication property, which is very important, which means that if you take the pointwise multiplication of two of these error correcting codes, you will get an object that resides in some other error correcting code, but also one that has good distance. You have another thing that's very important, which we'll call zero testing, or the ability to factor out certain, properties. So a polynomial p vanishes on a set of points h if and only if you can explain that by breaking up p into the product of two polynomials. And one of them is depending only on h. And it is actually the product of all x in h, or all little h in h of x minus h, which we will call the vanishing polynomial. So you have this ability to explain or demand explanations in the form of factoring polynomials. And you have succinctness, which means that in certain cases, for nice H's, for instance, when they are subgroups, you can actually evaluate this polynomial, this vanishing polynomial, very efficiently. And turns out that all of these properties are needed. If you take one of them away, then suddenly things become much less efficient or impossible. So this is a little bit about the mystery of like why polynomials, you know, they have all of these useful properties. There are a bunch of others. If you talk about Zk, they have this MDS property, which is also very useful, and I'm not going to mention it. So all of these very important, very beautiful properties come about in polynomials, and some of their related, you know, some of their relatives. And now we're moving to a world where we're not going to have like good old, let's say, univariate polynomials. And the question is, do we have all of these properties? So the nice answer is yes, you do have, and that's basically what's, you know, what appears in that beautiful paper. Go and read it. I'll give a little bit of intuition about what exactly is going on there. So let's recall the circle. The circle is the set of points x, y. Oh, okay, we're going to fix our field. Our field is the Mersenne prime 2 to the 31 minus 1. The circle is the set of all points x, y in this field, such that x squared plus y squared equals 1. And it turns out that this set of points actually forms a group. And maybe the simplest way to see it, or to verify it later offline, is to notice that, first of all, there's a complex extension of F31. The equation x squared plus 1 doesn't have a solution. So minus 1 does not have a root, just like over the reals, which means that you can extend the field to a degree 2 extension. With the reals, you would get the complex numbers. With this M31, you get the degree 2 extension. Then you can think of it as adjoining the you know, root of minus 1. And then it turns out that you move to a larger field, the degree 2 extension. And within that larger field, there's a multiplicative subgroup of size 2 to the 31 that maps to the unit circle over this base field by applying something known as the norm map. So there's a way to show that there's a group there, and there's a group operation that actually corresponds to also the geometric way you would add points on the real circle. And it has exactly 2 to the 31 points that reside you know, that we care about. Okay. So there are some operations that you can do with these points, or some definition. Every point has sort of its reflection or inverse, which is you know, just the point here. And you can double points, which if you would draw it this way, it would just be like adding up the angles. Again, I'm reminding you that we're not working over the reals, so this is just some representation. And you can project onto the x coordinate. And something that is really important, and again mysterious, is that you have two things that that you can sort of commute. You can double a point and project, or you can project and then double. So what do I mean? When you double a point, when you move from the point P to 2P, notice that the x coordinate depends only on the x coordinate of the previous point. And when you project onto x, it means you take the x coordinate. So what this means is that you can first project and then double, or do it the other way around. And this turns out to be extremely useful in making things more efficient. Okay. So the group would look like, you know, here's a group. The green points are a group. And then you could also move the group and get the red points, and that would be a coset. Now, some cosets are really nice in that you could have them so that when you project onto the x-axis, they come in pairs. So every 2 points are projected to the same point. And this is the set of points that we will take in order to evaluate functions and do low degree extensions and so on. So if in the FFT world we would have taken, let's say, the green points, and they would have been powers of a generator, now we're going to actually take you know, like the red points, a coset of them, with the property that each pair of them can be projected, you know, they can be divided into pairs that project onto the x-axis. And we call this a canonical coset. So what are going to be the analog of polynomials? We're going to look at bivariate polynomials, but we're going to take always them modulo x squared plus the curve, which means that you can represent any such function as basically f0 of x plus y times f1 of x, where both the functions f0 and f1 have bounded degree. And those are the functions we're going to take. Now, because we're evaluating things on the curve, Bezout's theorem actually shows that as opposed to standard polynomials, right, a polynomial of degree 1 will have exactly 1 root. Here, every polynomial that is of degree 1 will have exactly 2 roots because it will intersect the circle at 2 points. Okay, and then if you move to the projective version of this, polynomials have poles at 1 plus minus I. I don't want to go into this too much. So the code that we're going to take is a generalization of the Reed-Solomon code. It will be bivariate polynomials of total degree at most n, evaluated over the set of points that come on a coset of a circle, on a coset of a subgroup, on those red points that we saw. And then just like a polynomial of degree 1 has 2 roots, a polynomial of degree n will have at most 2n roots. And that is going to be our curve. That is going to be our code. Now there is a minor, as I said, I pointed out that there are like these minor things that need to be fixed. For instance, this code that we're using does not correspond exactly to what's known as a Riemann-Roch space, which is the natural generalization of polynomials. There's some extra dimension of 1 that is a bit tricky. I don't want to go into this, but the nice thing is that you can, well, here. The nice thing is that you can represent, remember that every function can be written as f0 of x plus y times f1 of x, and you have 2 endpoints. So a different way to think of this representation is to, well, let's say you can use these 2 points projected onto x to sort of break up your function into an f0 part and an f1 part, and make sure that each one of them has degree strictly less than n over 2. And that's basically the kind of code that we're working with. It's basically combining 2 polynomials of degree strictly less than n over 2 in a particular way that you can go back and forth between. And the reason this is useful is that you can just move very quickly between this bivariate polynomial to just a pair of polynomials. And you can start now applying things like FRI or FFTs or various things like that onto the projection. So basically, even though the real code is that we care about is like evaluated over these points on the circle, there is an alternative way of viewing things as just pairs of polynomials evaluated over specific points that happen to form this FF tree that you can apply FFTs to and evaluate things efficiently. So that's what I wanted to talk about there. And I'll end with just 2 questions that I hope someone will solve one day. Correlated agreement in bounds and concretely efficient modern PCPs or Starks. So the first one is related to the talk that Shubhangi just gave. She told you about this correlated agreement or proximity gaps paper. And there's this quadratic factor that we don't know what the right answer is. So we already proved this for agreement that is at least square root of the rate. But the question is, does it hold all the way up to the rate or doesn't it hold? And the answer to this question will determine what is the soundness level of all used Starks today. Like, are they a factor 2 off in terms of their security or not? And so that's a very interesting algebraic question. A second one, which is more high level, is that if you look at all of the stuff that is implemented today in practice, it pretty much relies on properties of polynomials in algebra. A lot of these were, had their starting points in the in the mid 1980s and 1990s. But there are like other techniques that come from combinatorics, things related to parallel repetition, direct product gap amplification, asymptotically good LTCs. And the question is, what about the concrete efficiency of these? Can someone take these techniques and construct a completely different, Stark or Snark or Snarg that is concretely efficient? Because they have been used to do marvelous things within theoretical computer science. So can you de-randomize these? That would probably be a way to make progress there. And I'll end with that. Thank you.
Questions?
So the way you're converting like the F31 to this pair of points, the addition operation takes what's supposed to be an XOR to be like 4 multiplications, right? So why is it efficient? So the way you define your group operation on the circle, it has 4 multiplications of F31.
Yeah.
Why is it efficient?
I think that in most cases, you never need to do these group operations when you're doing your FFTs and FRIs and so on. Basically, you have they are a way of indexing these tables, these code words. So for instance, so you never need to access them directly. It's, one place where you may need to access them is when you're doing these 2-to-1 transformations. They would show up, but if you project onto the x-axis, which is something that in CircleStark we do immediately, you now just sort of work with the x projections of those, and it turns out that now you're basically using twiddle factors and things that are just in the base field. So you never need to use the group operation in the computations you're actually doing.
So as a follow-up, maybe I missed, but what's the advantage of this transformation of the fields? Are you realizing that in the proof part, in the proximity?
Which transformation?
The transformation to pair of points.
Oh, the projection?
Yeah.
Yes, exactly. The projection means that now the twiddle factors don't need how do the twiddle factors come in? I guess think about the FFT. You say, I take this value and the next value, and there's something that's connected to the group operation that I take into account when I sort of do my FFT, right? So you would need, if you were working over the circle group, you're sort of, the next value would have needed to take both the X and the Y axis into them, and then you would have more multiplications. But if you project onto the x-axis and you work with a pair of polynomials of half the degree, then you're basically just manipulating twiddle factors on field elements, not pairs of field elements.
Yes. But I guess my question was more around why is it better than roots of unity?
Oh, because the roots of unity just won't have an FFT structure in this particular field.
Okay.
They won't have size 2 to the k, so you wouldn't have nice 2 to the 1 maps.
Oh, okay. Okay, thanks.
So do you know constructively how to find the coset that has this property? If you have the circle and you need to shift it, do you know how to find the shift?
Yeah, you would. One way is to, let's say, start with a group that is twice as large in size. Pick the first jump, make that the coset, and then just have the group be jumps of 2.
So spare me because I'm not a cryptographer. I have a different math background, but what properties do you lose, or is there any loss of kind of important properties as a result of switching to circle? I mean, it's a beautiful construct, but
what do you pay? What do you lose?
Yeah, in terms of like properties that existed on I think in the previous schemes.
Oh, the biggest one that is fixable but gets a little bit more complicated is like this vanishing property. Because every even line has immediately 2 zeros, so if you want something that just vanishes at a point, you don't get that. You can't like divide by one thing that vanishes at a point. You could get something that vanishes at pairs, and you could get like this, you can correct things by a ratio of like by a rational function, but it's a little messier than with polynomials where, and these things happen with algebraic geometry codes where you can get pretty much similar things, but now you use rational functions and it gets a bit messier.